In this video we're going to look at the antidifferentiation of e to the power of ax. Now we're actually going to look at a little bit more complicated formulas than this, but on the formula sheet this is the formula that you're given. The integral of e to raised to the power of ax dx is 1 on a e to the ax plus c. Now this doesn't have to be written like this. You can actually write it, if you like, as equal to e to the ax on a plus c, which is a little bit more compact. Anyway, other things that you need to remember are your index laws, things like anything raised to the power of 0 is 1, that if you have something raised to the power and you have a sum at the top, then it can be split into e to the ax times e to the b. When you multiply exponentials to the same base, you add their powers, and you can also do the same thing with division if you like, or you can leave this as something a little bit different. E to the ax minus b you can write as e to the ax times e to the minus b rather than the division. And this is still a constant as well. Okay, just a constant. All right, so basically it is a process of rearranging any function that you're given so that it's in this form so that we can apply this particular pattern. So let's have a go at some examples. So example number 1, integrate e to the power of 5x. So this is in exactly the format that it appears in our formula sheet. So if we follow our formula sheet pattern, we get 1 on 5 e to the 5x plus c. Don't forget the plus c. And if you want to write it as a single fraction, it looks like that. In the exam, either of these two answers is fine. Either of those two answers is fine. Okay, second one looks a little bit more complicated than the actual formula itself. The integral of 2 e to the 1 minus 2x dx. So this 2 is a common factor, so I can bring the 2 out the front, and then it starts to look a little bit more like what we had for our pattern. So we're going to use some of our index laws, and you can see I've got index laws over here. So e to the 1 minus 2x can be written as e to the 1 times e to the minus 2x. So that allows us to split this into two separate things to integrate, both of which are e to the power of x. So let's move this down and have a look. Now, we know e to the power of 1 is e, and that e is in fact 2.71. It's a constant. And so what I've got again here is I have a constant times by my function. So I can bring this constant out the front. And so I have 2e times by this integral here that we can just use our pattern on. So our a is minus 2, so our integral is equal to, I'll just change to a white pen, is equal to e to the minus 2x over minus 2 plus c. That's just using exactly the pattern that we had before. Now I'm going to multiply these two things together. So I have 2e, this is like on 1, if you like, times e to the minus 2x on minus 2. So the 2's will cancel. And that's going to leave me with an answer that is negative e times e to the minus 2x plus c, which is negative e to the 1 minus 2x. So I'm just going, using this idea here again, plus c. So our next example looks nothing like the formula that we've got, but it's got e to the power of. And so what we're going to do, we're going to use a little bit of our algebra skills here to separate it out so that it can look like multiple versions of e to the power of something that we can use our pattern on. So the first thing we're going to do is we're going to split this fraction, this denominator here, we're going to expand it out. Let's do it step by step. Let's expand out the the numerator, and then split it into two separate fractions, both over e to the power of x to the 4. Now, from here, we can simplify those two fractions using our index laws. So let's go ahead and to do that. So e to the power of minus x divided by e to the power of 4x is e to the minus x minus 4x, and it's e to the 0 minus 4x. Simplify those. Gives us e to the 5x minus e to the 4x, and I've separated them into two separate integrals so they look exactly like the formula, that pattern that we're using. You don't need to do that. If you wanted to do it as an integral, as just a single integral, you could have it as the integral of e to the minus 5x minus e to the minus 4x, and just apply the pattern to each of these terms individually as you go through. It will work out exactly the same. So let's go ahead and integrate those using the pattern, combine our plus c together and tidy up our terms. And if we did that using this other version over here, this bit here, this would be equal to e to the minus 5x on minus 5 minus e to the minus 4x on minus 4 plus c, which gives you minus e to the minus 5x on 5. This minus combines with this minus to become a plus e to the minus 4x on 4 plus c. Now, your answer in your back of your book might contain these with a common denominator and then, combine all sorts of fancy schmancy stuff. But my suggestion is, when you get to this stage here, if you're doing it by hand, double check your answer. With the CAS calculator answer for this, always put your answer equals to the back of the book answer. If it says true, see if you can figure out how to do it. If it appears too complicated, just leave it and move on. And our final example, example 4, is an application question where they want you to find a unique antiderivative. So again, they tell you something about the gradient function. They tell you that it passes through a particular point, and they want you to find the equation of the line. So we're going to use the relationship that the integral of the derivative is equal to the y value with our constant of integration. So let's go through and solve this, and let's integrate our derivative function. So just using our pattern on this term gives us e to the 2x on 2 minus, and this term here is e to the minus 3x. So using our pattern, e to the minus 3x over minus 3 plus c. So when we tidy this algebra up here, we get e to the 2x on 2 plus e to the 3x on 3 plus c. So that is our equation for our line, but we still have this plus c as the unknown. So we're going to use the point 0, 1 to substitute in to our equation, and we're substituting in our 0 where our x value is and our 1 where our y value is, given that our equation is y is equal to e to the 2x on 2 plus e to the 3x on 3 plus c. So we'll go ahead and substitute that in. The y value is a 1, the x values are zeros, and then what we're going to do is use our index laws. So anything multiplied, 2 times 0 is 0, so e to the 0, that becomes a 1. 3 times 0 is 0, e to the power of 0 is 1. There are our index laws at work. So we end up with 1 is equal to a half plus a third plus c. So to figure out what the c is, what I'm going to do is I'm going to write those two fractions with the same denominator. So you can clearly see that 1 is equal to 3/6 plus 2/6 plus c. So our c must be 1/6, which means that our equation overall has what we had before, what we came up with here, with our plus 6, or a plus 1/6 on the end. That is the equation of the curve.